Hey, Trip Zero here, and I'm going to conduct an experiment to test the performance of a geothermal water system. Specifically, how much energy can be transferred through the system any given second. So, just to go over the design of my greenhouse, on the left side here, I have a 16 by 6 foot greenhouse, 2 beds with a 3 foot aisleway, roughly 3 foot. It's like actually probably 2.5, but an aisleway in between. The middle section shows how the geothermal is laid out. It's a side profile, so if you can follow me describing, like, it goes into the ground 6 feet. It does this serpentine pattern, which is this lower image in the center, 9 inches apart, and then it goes up 1.5 feet and does the same thing. Then it comes back up. Once it comes back up, the far right image describes where it goes. It goes through the soil bed, through the aisleway, into a 55-gallon drum. Out that continues in the aisle about 3 inches deep, and then it goes back into the geothermal store. So that's basically the layout of my greenhouse. I'm going to measure. What I'm going to do is I'm going to take some colored water. I'm going to color it red. I'm going to measure exactly how much I have going into the system, and then I'm going to push the red water in. Right now there's this is a live greenhouse, so there's plants inside. There's existing water going through the system, so I've colored the water red to differentiate it, so I know when to start, measuring the time. And that way I can actually figure out how much water the system capacity is, which I've already done the math. It should be 7.6 kilograms it holds. So we'll go out and do that experiment. I'll have the red water pumped through the system. I'll measure the temperature before, and I'll measure the temperature after. And from that we can use some equations to figure out how many watts or joules per second is transferred, basically the cooling effect, how much energy is removed from the water, how much cooling it does. So we'll go out and do the experiment. Poured the water, red water, into this thing. We do have a slow leak, so I need to move quickly. The existing water and the new water is going to come out here. I'll fill the clear water, the existing water that's in the system, to this bucket. 45. And with this bucket, I'll swap them out. Swap them too. And this will go with the new water, and we'll measure the temperature there. I've got my assistant with me, Mr. Miggy, in his pajamas. I'll start the timer as soon as I see red to get initial reading. The water is reading 35.9, 36. This is hot water from the sink. And let's release this pressure. Miggy, can you hold this in there? Can you hold that right there? Thank you. Hold it tight in that bucket. Good boy. And we will turn on the power to our pump. Pump. Okay. And it's going. You see red. Changing to red. So let's keep an eye on this. And we'll start the timer. When it starts turning red, Miggy, when it starts turning red, you gotta lift that up and then put it in this bucket, okay? So we'll be able to time how long until that bucket, that black bucket's empty. That'll give us how much mass we can get through the system.
Nothing. Taking forever.
Keep it there. Actually, maybe I'll take a look at the times on this. It's probably better to measure the water that's coming out until it starts turning red. So I'll just get a reading on that from the video itself. Won't be as accurate, but that'll tell us our flow. You can see this red's kind of pink now. Is it changing color yet?
Wait. No.
Not yet. Just for kicks, we could probably measure that. There's our laser.
Oh, we're shining the laser.
We're coming out at 23. That doesn't give us much, but just for a baseline, I suppose. When it starts turning pink, that's when we want to measure the temperature delta so we can get how much energy the system, how much energy is being transferred into the geothermal system, how much cooling or effective heating this thing can do. I will measure this bucket I'll try and weigh this bucket, measure how much. Is it turning? Oh, is it turning? Turning pink, pink, pink. Put it in here.
What? Where?
Okay. Hold it up, hold it up. A little bit of spillage.
Really?
Move the green bucket. Oops, sorry. Got it? Okay, fill that up. So we got a little bit of pink in there, but pretty good, pretty good.
Washed on me.
Alright, so the water, the pink water coming out of there is 24. A little bit warmer than the water that was existing in the system. 24.9.
I'm covering water.
Yeah, this thing's running quite low. It's probably only got a few seconds left. So I think this tells us
It's dying on me. It's dying.
if I can. This gives us a kind of baseline.
Yeah, I got it. Stop shooting. Get you. Not stick. Instead, is it? Oh, it's.
Still got a little bit more. Let's go. I'll tip this so we can kind of get all of that emptied into there. Hold that up. So yeah, that not a whole lot of pink. Not as pink as it was before.
I'm gonna stop the water.
You're gonna stop it, huh? Miggy, can you grab the laser and point it at the water? Good boy. All right, let's see. Up to 26 now. We're just about run out of water.
6.5. 5.5.
And that's about all she wrote.
Oh my gosh.
Okay.
The water's out.
The water's out. Okay.
Is it done?
I think it's done. Okay, take the measurement. Shine the laser in there. What do we get? 25.6.
25.
About
That was a lot of water.
All right, 25.7. We're going with that.
Oh, it's the same size.
So we've got our data recorded, and I've measured how much red water we got out of the system. And I also measured the clear water that we got out of the system before the red water started. And so this was the number, the total before, 12.9 kilograms. And oddly enough, like if you add the output of the red water and the clear water, you get 13, which is right around the same number. So interesting. So I'm guessing, yeah, the system probably holds around 7 kilograms. Anyway, let's see. So I've got the start time, which was from the video 4:58, the end time 8 minutes 38 seconds, which adds up to about a total of 220 seconds. I have the beginning temperature and the end temperature recorded. And so we can use the equation Q equals MC and then the delta of the temperatures, where Q is the energy, M is the specific heat of water, and M is mass, and C is the specific heat of water. T1 and T2 are the temperatures. So this is what if you put in all those numbers, that's what it comes out to. So we can see our energy loss, total energy lost is about 328 watts, 329 watts rounded up. 328,000 watts. And we divide that over time because actually that's joules. Watts is per second. So we divide that over our time and we get 1,494 watts of energy transfer. So we just did the experiment. It's actually quite a few hours later in the middle of the night. So we found out that our system is about 1,500 watts. And we also found out that, over the course of about 3.5 minutes, it was able to take 30 degree water down to 26. So pretty good. I'm interested to see how that compares to other systems out there. Of course, I don't know of any other geothermal water system out there, so we'll see. Another thing is, given the square area the square, how many square meters the surface area of my greenhouse is. The solar input can be as high as like 8,000 watts, so, which is a lot of watts. And if we're only being able to cool and remove about 1,500 watts of that, that's a problem. So with 70% shade cloth, which I have now, we're that brings it down to about 2,200 watts or 2,400 watts. So we're getting pretty close, but that's still a lot of energy we have to remove. So I don't know if that means I need like a larger system, like twice as large, 2 times as large, or if I just need a twice as fast pump. I'm gonna have to do some research and figure that out. So that was a great experiment. I learned a lot. I'm gonna learn a lot more, and hopefully give some recommendations. And if anybody wants to repeat the system, hopefully this information will come in handy. So with that, Trip Zero out. See ya.